This is Ralph. I'm Lucas. This is Ryan, and that's Brendan. And for our senior design project, we converted natural gas to ammonia. We are making an ammonia plant. Ammonia is the second most produced inorganic chemical in the world. And we are converting natural gas to hydrogen and combining it with nitrogen to create ammonia. Our plant will be located in Philadelphia, Pennsylvania, because of its proximity to the Delaware River. This will give us easy access to ship and rail transportation, which will allow for more efficient importation of raw materials and exportation of product. Ammonia is used in industry in various ways. About 80% of ammonia is used for fertilizer, which is the most preferred nitrogen-containing nutrient for plants. Other uses include refrigerant gas and purification of water and many household cleaning solutions. Our plant will make about $20.8 million over the span of about 15 years, and we will produce about 775 million pounds of ammonia per year. And now I'll be handing it to Brendan, who will talk more about our process.
The first steps in the ammonia synthesis process include removing the impurities from our natural gas stream. So first, we run the stream through a mercury removal system, which is an ion exchange resin. This system flows through a cross-linked polymer to force contact with the exchange sites. So this process reduces the amount of mercury in the stream to less than 0.01 microgram per a nanometer cubed. The next step in our process is the sulfur removal. So this desulfurization unit is a packed bed of zinc oxide at 700 degrees Kelvin to remove hydrogen sulfide. This is an exothermic reaction, so a temperature control is put on that unit. So after it exits the sulfur removal unit, there's trace amounts of mercury and sulfur in the stream. So our next step is to produce hydrogen from methane. So to do this, we use a steam methane reformer where water is pumped in and reacted with the methane at a high temperature in order to produce carbon monoxide and hydrogen. So sometimes there are two reformers. We increase the temperature in our steam reformer to 1500 degrees to get a higher conversion of 95%. And this eliminates the cost of oxygen as a raw material, a second reformer reactor, and eliminates the need for a methonator later in the process. So we designed the steam reformer using two different reactors in HYSYS. First reactor was a conversion reactor, which put all the higher hydrocarbons and converted them fully into hydrogen. And then from there, we used a plug flow reactor to model a real SMR in a furnace. And so the plug flow reactor was ran at a constant temperature to manipulate the furnace. After it came out of the SMR, so we used a water shift reactor to convert water and the carbon monoxide to carbon dioxide and hydrogen. So this was done to create carbon dioxide, which is a less hazardous gas than carbon monoxide, as well as it improves our yield of hydrogen in the same process. So this is also an exothermic reaction, so there is a temperature control on this process as well. And this was modeled also using a plug flow reactor in HYSYS. We used equilibrium constants and temperature data to find a temperature that optimizes the conversion while still using a minimum amount of energy. And so that conversion came out to be 80%. And from there, exiting our water shift reactor, our stream is now mainly made up of carbon dioxide and hydrogen with only trace amounts of carbon monoxide and methane. So now I'll hand over to Ralph, and he'll discuss our hydrogen purification and ammonia synthesis.
The next step in our process is using a water knockout drum. This drum is necessary because it helps run our pressure swing absorption system more efficiently. Because we have this knockout drum, we will be able to reduce the size of the feed stream going into the pressure swing absorption, and there will be less water in the pressure swing absorption system, so it will not get flooded as fast. The knockout drum is modeled as a vapor liquid separator in HYSIS. This is done at a temperature of around 120 degrees Fahrenheit, and this separation separates about 95% of the water from the feed stream. There is a pressure control on this system to ensure that we don't overuse the system and have a large amount of pressure buildup in it. Following the knockout drum, we have our pressure swing absorption system. This system is comprised of 7 large vessels, and each vessel is packed with 5A zeolite absorbent. The unit we are expecting to build is modeled after the Gemini 9 model used by Air Products. This model separates both hydrogen and carbon dioxide from the feed stream. This system uses 13 different steps to complete this purification process, and it both increases pressure and depressurizes inside these tanks in order to purify the components. This system has a recovery of about 90% and a purity of 99% for both the carbon dioxide and hydrogen gases going through it. In HYSIS, we modeled this as a splitter, but this only accounts for recovery or purity. After we have our hydrogen stream, it is then sent to our ammonia reactor. Here it is mixed with a 3-to-1 ratio of nitrogen. The reactor is ran at about 840 degrees Fahrenheit and 200 atmospheres. This is both to obtain a moderate conversion and do it in a reasonable amount of time. We could run the reactor at a lower temperature to increase our overall conversion, but from literature we found that the rate of reaction will greatly decrease. This reaction is very exothermic, so this reactor will have to be jacketed somehow. There will also be a temperature control on this reactor. The jacket surrounding this reactor is going to be filled with water, and that water will be used elsewhere in our plant. Since there's only about a 40% conversion in our ammonia reactor, we have incorporated a recycle loop. This allows us to utilize our hydrogen and nitrogen gases to their full potential and create an overall greater conversion. The final units to note that don't appear on our block flow diagram are a compressor and a turbine in this cycle. From research, we found out that this ammonia synthesis loop is similar to a refrigeration cycle. So in order to get our pressure up to 200 atmospheres, we will need the compressor. After it goes through the ammonia reactor, we run the feed gas through a turbine. This helps cool our product, and it also aids in the separation of ammonia. The ammonia will then be further cooled, and it will be separated using a vapor liquid extractor, similar to the knockout drum. After the liquid ammonia is out of the stream, we still have the hydrogen and nitrogen. These will return through the recycle loop and make it back to the compressor, and this cycle will happen all over again. The energy produced from the turbine will then also be used to run the compressor. To explain the economics of this plant, I would now like to turn it over to Ryan.
So now that we have our plant modeled and sized, we want to see if our plant is actually economically feasible to build and to run based on the costs of raw materials and all our capital costs and literally all our fixed costs. So as a base case, we found that we modeled 92,000 pounds per hour of ammonia. And with ammonia selling around 340 pounds per ton, this equates to around 17 cents per pound of ammonia. So as I mentioned before, the capacity of our plant is around 92,000 pounds per hour. This equates to around 775 million pounds per year based on an operating time of around 8,400 hours per year. The total amount of capital that is used for this capacity is around $117 million. This accounts for all our equipment design and all our OBLs, which is our site development, our cogeneration system, our product storage, and our wastewater. Assumptions did have to be made before we started our cash flow diagram. So to begin with, our discount rate, since we are a specialty chemical plant, our discount rate was around 12%. With our income tax rate at 35%, our working capital or percent of revenues is 10%. Our inflation or escalation throughout the entire year of all the years of production is around 3%. SG&A and percent of sales is 1%. And as I mentioned before, our operating time is 8,400 hours per year. This accounts for downtime and any time of maintenance needs to happen on the plant. So to begin, we looked at the raw materials that needs to come into the plant. And total raw materials is around 9.39 cents per pound. And to look at this a little deeper, you have all our catalysts for all our reactors. These are fairly small amounts, and that's why there's no cent per pound produced calculated, because they're such low in demand throughout the rest of the plant compared to the other materials that we need. Our water, which is taken up from municipal city water, costs around 2.2 cents per pound of water, which equates to around 0.2 cents per pound of product as well. Our nitrogen, which is used for our ammonia reactor, is one of our main leaders in our costs of raw materials. And since nitrogen costs so high per pound, it equates to around 7.04 cents per pound of ammonia. Next, we have our byproducts of our system. We have cogeneration and carbon dioxide. Both of these can be sold or used elsewhere in the plant. Our cogeneration system uses a compressor and turbine to take the steam that is used from our 2 boiling feed heat exchangers, and 30% of that steam is generated into electricity, which we can use elsewhere in the plant. Also, from our PSA system, there's a high purity of CO2. This CO2 can then be sold at around 1 cent per pound produced, giving us around 0.83 cents per pound of ammonia. So our total byproducts is around 2.31 cent per pound of ammonia. Next is our utilities costs, which are mainly everything we need to keep the plant up and running, make sure everything's safe. Our total utilities is around 2.42 cents per pound of ammonia. And to dive in a little deeper, we have fuel, power, cooling water for all our reactors, refrigeration to condense our ammonia, and our wastewater costs for our water knockout drum. And more specifically, our power is around 3,800 kilowatt hours. 3,400 of this is to account for lighting and other equipment. So really what's left is around 400 kilowatt hours. This is fairly low for the amount of other equipment we have. And as Ralph mentioned previously, we have a turbine and compressor in succession of each other. So we can use the power generated from the turbine to help run the compressor, and that's why we have around 400 extra kilowatt hours that just need to be used. Also, we have our fixed cost. Our fixed cost is around 3.4 cents per pound of ammonia. One specific thing that we want to talk about in our fixed cost is our labor. We have estimated around 100 workers working in this plant, 80 of which are operators. There's going to be 20 operators per shift, a total of 4 shifts throughout the day. Around 14 of those operators will be working on the bigger scale equipment. We will have 2 operators per equipment, and the other 6 will be mainly operating the smaller heat exchangers and whatnot. That leaves around 20 other employees. The 20 extra employees will account for 10 of them will be engineers, 5 of them will be high management, and the other 5 will be more non-technical roles. We have accounting, nursing, stuff like that, and those all that are non-operators, they will occur on the first shift. So in total, our total cash cost is around 12.93 cents per pound of ammonia. We have, with the price of ammonia, around 17 cents per pound. And using our profit from our byproducts of cogeneration and CO2, we have 2.31 cents per pound. This leaves a profit margin of around 6.41 cents per pound of ammonia. This in total, after 3 years of construction and 15 years of production, we will have a total net worth of around $20.8 million. This gives us an RTROR of 15.06%. And based on the cash flow diagram, if we begin our startup in 2017, we will begin with a positive profit of around the year 2030. And now we'll turn it over to Lucas, who will begin our recommendations for this plant.
So as we stated earlier in the presentation, the plant made about $20.8 million over the span of about 15 years. So I would recommend to implement our plant because of the profit made. However, as time goes on, you have to, adapt to new technologies. So we implemented 3 scenarios that we could look at to better improve our plant. The first being to add a second water shift reactor to, help cut down on the carbon monoxide byproduct. A second scenario would be to utilize a water uptake mechanism with pumps and heat exchangers to source the water from a river rather than using the municipal water from the city. And a last recommendation would be to heat the water feed using the SMR instead of the ammonia reactor. Thank you for listening to this presentation, and I hope you take our recommendation to build this plant.